Good morning, everyone. The topic that I will discuss with you today is all about fracture toughness and fatigue testing. Fracture toughness and fatigue testing is the analysis of fractures of machine parts and structures that has revealed that in most cases, their fracture is due to material fatigue, which is known to be responsible for the initiation and propagation of fatigue cracks in the course of cyclic loading. Such cracks ultimately lead to complete failure of a component. A number of standardized tests have been devised to measure the fracture toughness values for structural materials. In the United States, these standard test methods are developed by the ASTM, or which is known the American Society for Testing in Materials. Procedures and specimen configurations for most tests are relatively complicated, and we will not attempt to provide detailed explanations. In brief, for each test type, the specimen of specified geometry and size contains a pre-existing defect, usually a sharp crack that has been introduced. The test apparatus loads the specimen at a specified rate and also measures load and crack displacement values. Data are subjected to analysis to ensure that they meet established criteria before the fracture toughness values are deemed acceptable. Most tests are for metals, but some have also been developed for ceramics, polymers, and composites. So what is impact testing? Impact test mechanics as a scientific discipline. Impact testing techniques were established to ascertain the fracture characteristics of materials at high loading rates. It was realized that the results of laboratory tensile tests at low loading rates could not be extrapolated to predict fracture behavior. For example, under some circumstances, normally ductile materials fracture abruptly and with very little plastic deformation under high loading rates. Impact test conditions were chosen to represent the most severely related to the potential for fracture. The first one is the deformation at a relatively low temperature. A high strain rate, for example, rate of deformation. And the last one is the triaxial stress state, which may be introduced by the presence of a notch. So bakit ba importante ang impact testing? Ang impact testing ay ang nagdedetermine ng amount of energy absorbed by a material during fracture. And this absorbed energy is a measure of a given material's toughness and acts as a tool to study temperature-dependent brittle to ductile transition, which I will discuss later on. It is to determine whether the material is brittle or ductile in nature. Why impact testing is done? Impact testing is used to determine material behavior at higher deformation speeds. Classical pendulum impact testers determine the impact energy absorbed by a standardized specimen up to break by measuring the height of rise of the pendulum hammer after impact. Types of impact testing. There are two kinds of impact testing, the ISO test and the Charpy test. In this video, I will discuss with you the difference between these two tests. Based on the position of specimen. So, kita nyo naman dito sa video kung ano ang pagkakaiba ng Charpy and ISO test based sa kanyang position. Ang position ng specimen sa Charpy test ay horizontal while on the ISO is vertically. Based on the direction of notch face, the Charpy test is opposite side of the striker, while on the ISO test, the notch is in front of the striker, or they rely on the same side. So now let's go on with their difference according to their notch face. On the Sharpie test, the type of notch used is in U-shape or U-notch, while on the ISO test, it is V-notch or V-shape. Sa Sharpie test, ang specimen na ginagamit ay 55 by 10 by 10 mm, while on the ISO, it is 75 by 10 by 10 mm. Type of hammer. Magkaiba rin sila ng type of hammer na ginagamit or yung striker. Sa Sharpie test ay ballpeen hammer while sa ISOD ay farming hammer. Based naman sa striking point or yung posisyon ng striker. Ang posisyon ng striker ay sa Sharpie test ay nasa center or katapat mismo ng kanyang notch face. While sa ISOD test, the striker is on the upper tip of the specimen. Material tested. Sa Sharpie, metals ang karaniwan nilang tinetest, while sa ISOD ay plastic and metals. So now let's go on to ductile to brittle transition. One of the primary functions of the Sharpie and the ISOD test is to determine whether material experiences a ductile to brittle transition with decreasing temperature, and if so, the range of temperatures over which it occurs. As may be noted in the chapter opening photograph of the fractured oil tanker for this chapter, widely used steels can exhibit this ductile to brittle transition with disastrous consequences. The ductile to brittle transition is related to the temperature dependence of the measured impact energy absorption. This transition is represented for a steel by curve. At a higher temperature, the CVN energy is relatively large, corresponding to a ductile mode of fracture. The temperature is lowered. The impact energy drops suddenly over a relatively narrow temperature range. Below, with the energy has a constant but small value, that is, the mode of fracture is brittle. Meaning, the ductile to brittle transition is affected by the temperature. As the temperature goes lower, the impact energy drops suddenly. This graph represents the ductile to brittle transition, the energy absorbed impact, and the temperature. At low temperatures, some metal that would be ductile at room temperature become brittle. This is known as a ductile to brittle transition. The ductile to brittle transition temperature is strongly dependent on the composition of the metal. Steel is the most commonly used metal that shows this behavior. For some steel, the transition temperature can be around 0 degrees Celsius, and in the winter, the temperature in some parts of the world can be below this. As a result, some steel structures are very likely to fail in winter. So, ang best example daw ng materials sa ductile to brittle transition ay ang steel. The best example for the ductile to brittle transition is the sinking of the Titanic ship. So, lahat naman tayo ay very familiar sa paglubog ng Titanic ship. The sinking of the Titanic ship was caused primarily by the brittleness of the steel used to construct the hull of the ship. And dahil sa icy waters sa Atlantic, the steel was below or nag-undergo siya sa ductile to brittle transition temperature. The impact of an iceberg on the ship's hull resulted in brittle fracture of the butts that were holding the steel plates together. So we have to remember na even a small impact can cause a large amount of damages. The next one is destructive testing. Destructive testing is undertaken in order to understand a specimen's performance or material behavior. These procedures are carried out to the test specimen's failure. Destructive test procedures are carried out to the test specimen's failure. Destructive testing procedures can either follow specific standards or can be tailored to procedure set service condition. Destructive testing methods are commonly used for materials characterization, fabrication validation, failure investigation, and engineering critical assessments. Types of destructive testing. The first one is the aggressive environment testing. This includes the fracture and fatigue testing in SAR, sweat, and other corrosive environments, as a range temperature and pressures. These tests allow industries to assess the impact of this condition on material and performance. The next one is the corrosion testing. This covers non-toxic, small-scale, aqueous corrosion testing in a variety of different environments including fresh seawater. Fracture and mechanical testing includes different types of destructive testing methods such as tension test, sharp impact test, Bellini drop weight testing, field test, crush testing, pressure and fracture testing, as well as the testing of materials. Fracture and mechanical tests can be carried out on different materials such as welded polymers, including plastic pipes. Fatigue testing, performed in air or seawater environments. These tests are used to test parent materials and the endurance of welded joints under constant or variable amplitude loading. These destructive testing methods can also be used for fatigue crack growth, testing of welds, base metals, and heat-affected zones. The next one is the hydrogen testing. This type of testings covers materials that have been risk of corrosion from exposure to hydrogen. Parang yung corrosion testing din siya. This test can be carried out at a variety of different temperature and strain rates. The last one is the residual stress measurement, are those that remain in a solid material after the original causes of any stresses have been removed. This can be intentional, such as with a scratch-resistant glass on smartphones, or unintentional, which can lead to premature failure of a structure. Measurement of residual stresses allows for designers and engineers to determine the factors like near surface and true thickness residual stresses distribution, which can be used in engineering critical assessments. Fatigue. Fatigue comes from the Latin word fatigare, or to tire. Fatigue is a form of failure that occurs in structures subjected to dynamic and fluctuating stresses. Under these circumstances, it is possible for failure to occur at a stress level considerably lower than the tensile or yield strength for a static load. The term fatigue is used because this type of failure normally occurs after a lengthy period of repeated stress or strain cycling. So, hindi lang siya sa tao nangyayari, hindi lang para sa taong salitang fatigue, kundi pwede rin siya sa isang material. Fatigue is important inasmuch as it is the single largest cause of failure in metals, estimated to be involved in approximately 90% of all metallic failures. Polymers and ceramics, except for glasses, are also susceptible to this type of failure. Furthermore, fatigue is catastrophic and insidious, occurring very suddenly and without warning. Fatigue failure is brittle-like in nature, even in normally ductile materials, in that there is very little, if any, gross plastic deformation associated with failure. The process occurs by the initiation and propagation of cracks, and typically, the fracture surface is perpendicular to the direction of the applied tensile stress. Fatigue properties of materials are often described the fatigue limit or the SNN curve. Ito yung SNN curve or the Waller curve. It describes the relation between cyclic stress, amplitude, and number of cycles of failure. SNN curve are derived from the fatigue test. The tests are performed by applying cyclic stress with a constant amplitude on the specimen's unit failure of the specimen. What are the factors that affect fatigue life? The first one is the mean stress. The dependence of fatigue life on stress amplitude is represented on the SNN plot. Such data are taken for a constant mean stress Sm, often for the reverse cycle situation. Mean stress, however, also affects the fatigue life. This influence may be represented by a series of SNN curves, each measured a different Sm, as depicted schematically in Figure 8.25. As may be noted, increasing the mean stress level to a decrease in fatigue life. The next one is the surface effects. For many common loading situations, the maximum stress within a component or structure occurs at its surface. Consequently, most cracks leading to fatigue failure originate at surface positions, specifically stress amplification sites. Therefore, it has been observed that fatigue life is especially sensitive to the condition and configuration of the component surface. Numerous factors influence fatigue resistance, the proper management of which will lead to an improvement in fatigue life. These include design criteria as well as various surface treatments. Next is the design factors. The design of a component can have a significant influence on its fatigue characteristics. Any notch or geometrical discontinuity can act as a stress raiser and fatigue crack initiation site. These design features includes grooves, holes, keyways, threads, and so on. The sharper the discontinuity, for example, the smaller the radius of curvature, the more severe the stress concentration. The probability of fatigue failure may be reduced by avoiding these structural irregularities or by making design modifications by which sudden contour changes leading to sharp corners are eliminated. For example, calling for rounded fillets with large radii of curvative at the point where there is a change in diameter for a rotating shaft. Surface treatments. During machining operations, small scratches and grooves are invariably introduced into the workpiece surface by cutting tool action. These surface markings can limit the fatigue life. It has been observed that improving the surface finish by polishing enhances fatigue life significantly. One of the most effective methods of increasing fatigue life performance is by imposing residual compressive stresses within the outer surface layer. Thus, a surface tensile stress for external origin is partially nullified and reduced in magnitude by the residual compressive stress. The net effect is that the likelihood of crack formation and therefore of fatigue failure is reduced. Residual compressive stresses are commonly introduced into ductile metals mechanically by localized plastic deformation within the outer surface region. Commercially, This is often accomplished by a process termed shot peening. Small, hard particles of diameters within the range of 0.1 to 1.0 mm are projected at high velocities onto the surface to be treated. The resulting deformations induces compressive stresses to a depth of between 1/4 and 1/2 of the shot diameter. The influences of shot peening on the fatigue behavior for steel is demonstrated schematically. Fatigue testing. It is defined as the process of progressive, localized, permanent structural change occurring in material subjected to conditions that produce fluctuating stresses and strain at some point or points that may culminate in cracks or complete fracture after sufficient number of fluctuations. Nomenclature to describe the test parameters involved in cycling loading. Fatigue is the progressive, localized, permanent structural change that occurs in material subjected to fluctuating stress and strains that may result in cracks or fracture after a sufficient number of fluctuations. The cyclic stresses are normally well below the yield strength of the material. The process of fatigue consists of three stages. The first stage, the first stage is the initial fatigue damage, or which the leading to crack nucleation and crack initiation. The second stage is the progressive cyclic growth of a crack or crack propagation until the remaining uncracked cross-section of a part becomes too weak to withstand the loads applied. And the last stage is the final or sudden fracture of the remaining cross-section. These are the types of fatigue failure. The first one is the mechanical fatigue, creep fatigue, thermomechanical fatigue, corrosion fatigue, and breathing fatigue. Mechanical fatigue is the fluctuations in externally applied stresses or strains, while the creep fatigue is the cyclic loads at high temperatures. Thermomechanical fatigue is the fluctuations in temperature as well as the stresses and strains. The corrosion fatigue is the cyclic loads in chemically aggressive or embrittling environment. Breathing fatigue is the cyclic loads combined with frictional sliding. Cyclic loading generally produces failure however low the stress may be. However, with some materials with the SNN curve levels off, suggesting that for these materials, a limit of stress can be specified, known as the fatigue limit, below which the infinite life can be expected. The fatigue life is thought to be associated with the phenomenon of strain aging. Most non-ferrous alloys do not show fatigue limit. Instead, their SNN curve continue to drop at a slow rate, or the dotted line. For these types of materials, the fatigue strength is quoted. This is the value of stress to which the material can be subjected to for a given number of cycles. Strain life approach. Low cycle, high stress fatigue with appreciable plastic deformation. So pag low cycle daw ay high ang stress fatigue. Uses the cyclic strain range versus number of cycles to failure. Total life is equal to crack initiation plus crack propagation. Failure is equal typically a crack of predefined size. The strain life relationship as follows. So ito yung formula niya. Where the constants in the equation are SF is the fatigue strength coefficient. E is the elastic modulus. B is the fatigue strength exponent, and EF is the fatigue ductility coefficient, and C is the fatigue ductility exponent.
Stress life approach. High cycle, low stress fatigue. Samantalang kanina kapag low cycle ay high stress fatigue. Material deforms elastically. Cyclic stress range versus numbers of cycles to failure or the SNN curve. Total life is equal to the crack initiation plus crack propagation. Failure is equal to the total separation of specimen. First fatigue design method, large amount of data available. Damage to tolerant approach, assume defects present in material. Linear elastic fracture mechanics approach, or the dA over dN versus delta K. Resistance to fatigue crack group. Useful fatigue life is equal to the number of cycles to promote a crack from an initial size to some critical dimension. Failure is equal to the critical crack size based on the fracture toughness of material, limit load for a particular structural part, allowable strain change in compliance of a component, etc.
For a clearer idea about the fatigue and fatigue testing, here is a video presentation for you.
Fatigue, variously defined as exhausting the strength or power of recovery, the deterioration of a material under repeated loading, and in the structural sense, the formation of a crack or cracks as a result of the repeated application of loads, each of which is insufficient by itself to cause normal static failure. Not one loading cycle, not 100 or a few thousand, but possibly millions and millions during the life of the structure. Examples exist throughout engineering. Structures large and small, dynamic and static. They all endure fatigue loading, and as such, have a fatigue life. We can examine fatigue cracking safely in controlled laboratory conditions. Take this beam, for instance, a model box girder in a 4-point bending test. The test machine applies a preset load once every 5 seconds. Now, although the stress developed is easily within the elastic range of the material, and the load sustained safely, repetition of the stress ultimately leads to cracking, often at welded joints. Because they appear after repeated loading, they're known as fatigue cracks. Excavator components are largely welded fabrications. Parts are tacked together, then fully welded using MIG or submerged arc welding. In service, they're subjected to a heavy load every time the bucket digs into the ground, which, as we see, is pretty frequently. So the component's design, welding and inspection must reflect this fatigue loading. Small portable parts can be tested in the severest conditions in the lab. But if the job is large and in full-time service, like a bridge support, a pipeline or an aircraft wing, then that's impossible. We need information at the design stage to predict the likely fatigue, wear and corrosion behavior of the structure. And we can gather this by laboratory tests of individual welded joints. Here we use a flat plate in simple tension with attachments on either side. The longitudinal fillet welds contribute little, but we'll see they pose a significant threat to the fatigue life of the specimen. But first, a simple tensile test. Elastic deformation is followed by plastic deformation. necking becomes evident and ductile rupture occurs. At a load corresponding to the material's tensile strength, it leaves a characteristically irregular fracture surface. Now, contrast this with a similar specimen in a fatigue test. A cyclic tensile stress is applied hydraulically. Eventually, it causes fatigue cracking, just here at the end of the weld. But the crucial thing is that this has happened at a stress well below the elastic limit. Here, fatigue cracking appears at the weld toe because of the local stress concentrations and also small weld imperfections. We can clearly watch a fatigue crack growing by testing this aluminium plate specimen in a fatigue test machine. By compressing time, we can speed up the view of crack growth. The test piece has an artificial stress concentration so that the crack is located accurately. By polishing the surface, we can see the crack propagate. First 10 millimeters, then 30 millimeters, to final failure. So, in service, it's important to inspect for evidence of fatigue early in a structure's life, close to load-carrying members where the cross-section changes abruptly. Of course, rust, dirt or paint can make this site job a tough and onerous one. If it's not spotted, a crack will grow progressively until the remaining cross-section can no longer support the force applied and rapid ductile or brittle fracture occurs. Fatigue crack surfaces have a distinct look about them. A smooth appearance around the point of initiation and well-defined steps corresponding to the last few cycles just before fracture. In practice, a degree of redundancy is often present in engineered structures. So, a redistribution of stress takes place, and the propagation of a crack may be slowed down or even halted. There's no danger of collapse, but the structure's stiffness may have deteriorated to an unacceptable level. What tests like this do is give a quantitative result of how many cycles produce a sizable crack. So we can now represent this graphically. Numbers of cycles, n, horizontally, and applied stress range, S, vertically. Log-log scales are used, with the horizontal scale up to 10 million cycles in this case. By testing several specimens at different stress levels, we can create a mean line for fatigue performance. The required life of the joint, expressed as a number of stress cycles, can be related to the allowable stress range for the particular joint. If the stress level is raised, a shorter life must be accepted, or, of course, the joint design changed. Different welded joint designs give different fatigue performances. The design of this lamppost, for instance, includes a stress concentrator, which has created an unpredictable fatigue behavior. So far, we've only looked at tests where the stress cycles are of equal magnitude, what's called constant amplitude loading. Of course, in practice, they're often very different. This bridge carries both heavy trucks and small cars. So, it's only by testing welded joints under variable amplitude loading, typically using a computer-controlled machine, that we can simulate actual service behavior. Fatigue cracks produced under variable load are usually characterized by beach marks, centered around the point of initiation.